Assignment 21. This is 3.5. Displacement, velocity, and acceleration. So your essential question, how do you find an equation for velocity and for acceleration given an equation for displacement of a moving object? So for those of you taking physics, this is going to tie in really nicely. I think the two subjects relate really well right now. In physics, you'll be doing all of this stuff with algebra because you're taking algebra-based physics, but you can also use calculus. And when you get to college, you might take calculus-based physics, or you can even try using some of these concepts in your algebra-based physics class. Okay, so let's define these things. What the heck am I talking about? So, displacement. So this is basically directed distance. So it's distance in a certain direction. So let's use an equation. How about one of a projectile, something, going up in the air and coming down? Okay, now we'll talk about velocity. So velocity has both speed and direction. So you have a rate happening, right? So velocity is basically the rate of change of your displacement, of your distance that you've traveled, okay? So if it's a rate of change, and if it's an instantaneous rate of change, then that must mean that it is the derivative of displacement or in other words, it is the instantaneous rate of change of displacement same thing, right? If we're talking about the speed, then we're talking about, there's not really a direction with speed. Okay, so if you wanted to think about the speed, then basically you want the absolute value of velocity, because velocity is going to have a direction. Oops. I didn't want that. So if you're moving forward, it's positive. If you're moving backward, it's negative. So therefore, if you're just talking about speed, it doesn't matter what direction you're going in. We usually, to find the velocity, we're going to talk about the derivative of my displacement function, which here is like a y, with respect to time. So when you're taking the derivative now, it's usually going to be, instead of with respect to x, it's going to be with respect to time. And it's always going to give you some kind of rate or speed, like feet per second. And so if I wanted to think about taking the derivative of this, okay, so the derivative of the function y, the displacement function y, with respect to time, well, how's that going to work? I'm basically going to use my power rule, right? So I'm going to bring down that 2. I'm going to end up with negative 32t. Oops. 32t plus, and then I'm going to take the derivative of the second piece, which is just going to be 37. Okay, and this is the same thing as velocity. So when we take the derivative of displacement, we get velocity. Okay, so the derivative of displacement equals velocity. So this is the derivative of the displacement. Okay, so what happens when we take the rate of change of our velocity? So what happens when we take when we ask ourselves, how fast is my speed increasing or decreasing? What's the rate of change of my speed? So think about that for a second. If I'm changing my speed at which I'm going, what's that rate of change of my speed? That rate of change of your speed is going to be acceleration. So this then is the derivative of velocity, because it's the rate of change of your velocity. Okay, so we can also think of this as the second derivative of displacement. So if you take the derivative of displacement twice, the first time you'd end up with velocity, the second time you'd end up with acceleration. So it's basically the instantaneous rate of change of velocity, which means taking the derivative of velocity. So if I take the derivative of velocity with respect to time, those units are going to be, and we've already done this in chapter 1 when we did all of our explorations, and we were looking at taking different rates of change, I guess average rates of change. But when we found the rate of change of velocity, we ended up with feet per second squared. Right? Because if you think about time and miles per hour, and you think of some curve here, right? And I take the slope of a tangent line. Well, my rise is miles per hour. My run is time. So, and I did this in chapter 1, but if I have miles per hour, let's say, right, then isn't this going to give me miles per hour squared? Okay, so in this case, it's feet per second squared. Just different units being used. So if I want to take the derivative then, let's call this, so maybe I can rewrite this as, well then my velocity here is negative 32t plus 37. And I should say my velocity with respect to time, so my velocity where my input is time. Okay, well now I want to find the acceleration. So basically I'm going to take this velocity function and I'm going to take the derivative with respect to time. Okay, so in this case, my dv dt is going to be my second derivative of my displacement, right, because there's one derivative. Or I can just now take my velocity function and take the derivative of that. So that ends up giving me just, well, let's see, there's a 1 there, so negative 32. Okay, and this is your acceleration. So if you wanted to write it as a final function, your acceleration function is negative 32. Which, you know, depending on what your units were, so let's say it's feet per second squared. Okay, so maybe I'm decreasing my acceleration by 32 feet per second squared. Okay, so let's talk about what it looks like to have second derivative notation. So, second derivative notation. You can see this a couple of ways. So you might see f double prime of t. You might see y double prime. Or probably what I'm going to use a lot is the second derivative of y with respect to time squared, which would be the same thing as taking the derivative with respect to time of the derivative of y with respect to t. Okay, so these are all different ways of writing this. Okay, so you might see f double prime, y double prime, and that would basically be, again, if I started with displacement and I wanted to get straight to acceleration, I might just write, you know, I'd have to take the first derivative, which could be like f prime, or y prime, or dy dt, and then I'd have to take the second derivative, so I may just write f double prime of t. Or I might write the second derivative of y with respect to time squared. Okay, so that's the dt. So I'm going to do example number 1, and I'm actually going to get that from your book. So it's problem number 2, page 97. This is the equation that they give us, and the directions say to find the equations for the velocity v and the acceleration a of a moving object if y is the displacement. Okay, so this right now is my displacement. All right, so my velocity is the first derivative. So it's basically the derivative of y with respect to my input is time. Okay, and that is going to be, so now I just basically do the power rule, because that's really all you guys know right now. So I'm going to have negative 1.2 t to the negative fifth minus, and then taking the derivative of that, minus 5. So that's your velocity function. Now in addition to that, we need the acceleration function. Now acceleration is the derivative of velocity. So that means I'm going to take now the second derivative of y. So I'm going to take the second derivative of y with respect to time. Okay? Or another way that you might see that, I could say, let me take the derivative of velocity with respect to time. These are d's, by the way. Or maybe I could say, these are all equivalent. You do not have to write these each time, but I'm just giving you some different ways that you might see it. Because another way was, I originally started with y, and now I want y double prime, or the second derivative. Okay, so let's actually do that. So now I need to go to velocity here, and I need to take the derivative of the velocity function. So when I do that and I bring down this negative 5, I'm going to get a positive 6 t to the negative 6. Okay, so really, your answer is really this, or it could have had any one of these before it. And here your velocity, we'll go ahead and we'll just circle this part. Okay, so how do you know if something is speeding up or slowing down using calculus? So let's talk about that. So speeding up or slowing down. And again, I really encourage you guys to read your textbook. I know it doesn't seem that great of an idea, but there's a whole bunch of great examples in here. And there's a whole bunch of great information. I mean, if you look at this book, it's written. It's a lot to read about. Okay, so I would highly recommend reading through this book because you can only get so much from me. You can only get so much from my abbreviated notes. Anytime that you're struggling with a concept, it would be a really good idea to have that third try, and maybe looking in your textbook and reading some of it might be helpful. So this is discussed on page 94, and it's got some visuals, which is really helpful. There's kind of this green box here. Okay, so and this is basically what we're going to write down. So if velocity and acceleration have the same sign, then we know that it's speeding up, right? The velocity is positive, okay, and my acceleration, the rate of change of velocity, is also positive. Okay, then I know that we're speeding up. Or maybe the velocity is negative, which means I'm going in a backwards direction. Okay, and the acceleration is also negative, so that rate of change is going in that same direction. Okay, that object is also going to be speeding up. However, if they have opposite signs, okay, so if velocity and acceleration have opposite signs, the object is slowing down. So if I have a positive velocity, but my rate of change of velocity is negative, then that tells me that my acceleration, right, I'm not going any faster, I'm starting to slow down. Okay, so, and these are kind of helpful little diagrams to look at. Okay, so basically, just a little note on that, you are speeding up if velocity and acceleration have the same signs. You are slowing down if velocity and acceleration have opposite signs. Okay, we'll do one more example together. I'm going to do another one from your book. So this one's going to be number 4 from that same page, page 97. Okay, so this example talks about parametric mode. Parametric. You've never graphed like this before, so it's going to be quite interesting. All right, and we are given this equation, x equals t to the 4th minus 11t cubed plus 38t squared minus 48t plus 50. And we are told that t must be greater than or equal to 0. Okay, so there's a lot to this, and you're about to learn a whole lot of new information. So let's look at this problem. Okay, you have an object moving in the x direction, right? So horizontally, with displacement, x of t, in feet from the y-axis. Okay, so starting at the y-axis, and then keeping your t being positive, so t is always positive time, and then moving along that x-axis. With your grapher in parametric mode and path style, plot the path of the object. Okay, so let's first find where parametric mode is. Okay. So I'm going to pull up my graphing calculator here. So it's parametric mode, which tells you that you probably want to go to mode. Okay, and if you look under where it says function, there's a par in there, or a parametric. That's what you want to press enter on. Okay, that's the mode that you want to be in. So it's parametric mode. Okay, you might want to take some notes on this. I'm not going to write it down because I already know how to do this. So you guys need to take some notes. Okay, now I'm going to actually put, oh, notice how it changed it? So you've got your x of t, and then you've also got this y value. So this is where you're going to, the y value is where you're going to watch this particle move. So if we let it just move along the x-axis, it's going to be really hard for us to see. So maybe we can move it up a little bit and just go along the line y equals 1. For x of t, I'm actually going to plug in the equation that's in the book. So watch how this is what you've been wondering. How do I get those t's to work? So, ooh, look at that. T raised to the 4th power minus 11t cubed plus 38t squared minus 48t plus 50. Okay. And it also said that we needed it to be in path style. So the way that you do path style, you want to, this is like your line style over here. So you want to use your arrows to get back over. Maybe I could have done it before I typed it in. And you're actually going to press enter to shuffle through. So now that's a darker line. Now that's your path style. So it's this weird, I don't know, a dash with a circle next to it. Okay, so path style has the dash with a circle. Okay, so you might want to, it looks, I don't know if you're going to write it down. Maybe it looks like that. Okay, so this is path style, which basically means it's going to follow a path. You're going to get to see it kind of move around on your screen. We need to think about our window. So, for example, we were told that t is also always going to be greater than or equal to 0. So we need to think about what is, where is this thing starting if time is 0? Well, if I plug 0 in for all of these, then I'm probably starting somewhere at 50 on the x-axis. So that's pretty important to think about. And then the fact that I'm also going to be focused on this y equals 1. Okay, it's basically going to be a particle moving like this on the line y equals 1. Okay, so let's make sure that our window looks good. So my t min will be 0. That's good. My max, we could probably make this go a little bit. It says time. It doesn't give like a specific amount of time. So how about we go 10? And we'll let it step pretty small. That way we can see it happen a little bit better. Let's see, your book, when they did an example, yeah, they used a tenth. Okay, and they also went, their time was from 0 to 10. So we'll leave it like this, and we could maybe go a little bit smaller, but I think that that's good enough. So my x value, let's see here. Right now my x value is a maximum of 45, but I had said that we were going to even start at 50, right? So I need a bigger max. So why don't I try 100, see what happens. Okay, and then I'm going to, oh, and I don't really care about my y min. So actually, I can leave that at 0. Okay, so I'm going to go ahead and graph this. Oh, look at that weird thing. Okay, so hopefully you caught that. There was some change in direction. Okay, so that's pretty interesting. So let's look at the rest of these directions. Let me move my graphing calculator. Okay, so what we need to do is we need to write a paragraph describing the motion. We need to include the approximate times and places at which the object reverses direction and the time intervals during which the object is traveling to the right and to the left. A sketch may help. So I think that's the first thing I'm going to do. And I'll tell you what else is probably going to help me with this is looking at a table so that I can see exactly where things are turning around, where they're getting bigger and smaller. Okay? All right, so I'm going to start by, and I believe you have to redo this. I don't think I can just have it. I got to kind of move around over here. But my goal is right now, what I'm trying to get out of this is just because that kind of happened fast for me. So I'm just trying to get an idea of how this thing was moving. Was it moving to the right? Was it moving to the left? What was going on? Okay, so let's see if this will graph for me again. I may have to go back and change something. Yep, I'm going to have to change something. So how about if I just, let's see. Let's go over here and we'll make it 10. Oh, graph that real quick. And then don't just ignore that. Isn't that kind of cool how that works though? And then I'm going to go back and I'm going to change. Oops. Oh no. Okay, my panic mode is gone, so I'm just going to change this back to 11. All right, so we got to pay attention. I think that's what it was. Yes. Okay. Here we go. So it happens quick. I'm going to graph it. Left, then right, then left some more, then all the way right. So we went left, then we did a little right, then we went some more left, and then we went all the way right forever. Okay, so it kind of looked like that, right? And so this was, the first thing, then it did this, turned around, then it did that, then it did that. Okay, so the question is, when did it do all of these things, and what exactly was happening? So I find it really helpful to look at kind of an input-output chart or a table where I can say, well, at this time it was doing this thing. Okay, so at time 0, I'm pretty interested in because that's where we're actually starting, right? At time 0, what's happening? Okay, so let's look at a table here. So I want to make sure that I am going to be at 0. We can go up by 1. I may need to change that a bit, but let's just see what's going on with our table. Okay, so at time 0, I am at 50, and this is in, I believe they said it was in feet. Yep, feet. So you are at 50 feet at time 0. Okay, and we are headed left, right? So we're heading left at that point. Okay, so at like 1 second, we're at 30 feet. So it looks like we're still heading left here, correct? Okay, so the question is, I know at some point this thing turns around. Well, when the heck does that happen? Because all of a sudden, I just went from being at 30 feet, that at 2 seconds, now I'm going back right again. So somewhere between 1 and 2, this thing turned around. So now that's my goal, is to figure out when does this thing turn around, okay? So I might want to get a little bit more detailed and go in maybe with tenths. See a little bit more information here. Let's see if that'll help me at all. So I'm getting smaller, so which means I'm heading left, right? My distance from the y-axis is getting smaller, smaller. I think it just got bigger, right? It went from 30 to 30.003. Now, that's not very far, so I'm pretty happy with the fact that at 1.1 seconds, this thing turns right. Okay, it turns back around. So at 1.1 seconds, I'm now at 30.003 feet. So I think it just turned around somewhere. So it turns right. If you want to get into more detail and really explore this, you totally can. Okay, so now the question is, well, for how long is it going right? Okay, because eventually, according to this, it's going to go back and go left. It's not, from what I remember, it was really short that it was going right, and that turned around and it went back left for a little while. Okay, so let's see if we can figure out where that happens. So I think I might just keep going. So it's getting bigger now, which means it's heading to the right. And I think it just ended up getting smaller, right? So 2.4, 2.5, it seems like it's heading back left. You can get even more in depth here. Okay, you can go to the hundreds, you can go to the thousands, but I'm going to say at about 2.5 seconds, it decides to turn around again. So at 2.5 seconds now, I'm going to be at 34.688, and that's when it turns left. Okay, and then let's see. So I should be getting smaller and smaller and smaller. Looks like I'm still getting smaller. Still getting smaller. And it looks like I just went bigger again, right? So I went from 4.8 seconds. I was at 9.44, so getting smaller from the time before. And then at 4.9 seconds, now I'm getting bigger again. So it looks to me that at 4.9 seconds, this thing now starts to turn right. Okay, so at 4.9, I'm at 9.5211 feet, and now it is turning right. And I believe it turns right for the last time, right? So I should see one turn here, two turns, three turns. And that's basically what I have. Okay, it was heading left, then it turned right, then it turned left, then it turned right, and it went on forever in the right direction. And you can see that this is just going to keep getting bigger and bigger and bigger. Okay, so you would need to explain that in some way. And I'm going to not do a bunch of writing, so you can pause this. But basically, you want to explain that, hey, this thing at time 0 started off at 50 feet, and it was heading left. And I noticed that it kept heading left until it got to around 30 feet, where that was at about 1.1 seconds. We can conclude that it probably turned right. So somewhere between 1 and 1.1 seconds, it turns right, because now we see that it's getting further and further and further away from the y-axis until about 2.5 seconds, where it ends up turning left again. And then it starts heading left until about 4.9 seconds, at which point it turns right again, and it goes right for all future values of t. So for time getting very large. Okay, and you can write that in your own words.